Okay, this video is going to introduce you to the ideal gas law. The difference between the laws we've been doing and the ideal gas law is that Boyle's, Charles, and combined all required that you have a before and an after scenario, and that the gas remained trapped. In the ideal gas law, we're going to be able to take a snapshot of a particular sample of gas at a particular moment in time. First thing we need to know is what exactly is an ideal gas. An ideal gas is a gas that follows the gas laws at all conditions. It also follows the kinetic theory exactly. And because of these two requirements, an ideal gas does not exist in reality. Why not? Well, first of all, one of the things the kinetic theory says is that gas particles are assumed to have no volume. And we know that gas particles are matter, and all matter has volume. So we run into problems when we get to certain conditions. And what conditions are these? Real gases will only be different from ideal gases at extremely low temperatures, such as those close to absolute zero, and extremely high pressures. Because at a low temperature and at high pressure, the gas particles would be packed tightly together, and the volume and interactions would start to come into play. As long as we're under most conditions, real gases and ideal gases act very similar, which is why we're able to use the ideal gas law to describe gases. Because most of the time, we're working at what we call close to STP, standard temperature and pressure. And standard temperature and pressure is always 1 atm, which is normal atmospheric pressure, and 273 Kelvin, which is kind of cold. It's about 0 degrees Celsius, but we're within the range at normal room temperature. So what is the ideal gas law? The ideal gas law is the equation PV, pressure times volume, equals nRT, number of moles times the constant times temperature, sometimes referred to as the Puvner rule, because that's what it says. Looking at each of the parts, R is the ideal gas law constant. Constant means it's the same number at all times as long as the units match. And for our purposes, we're going to use the value 0.0821, and that has a unit of liter atmospheres per Kelvin mole. Pressure is P. It has to be in atmospheres to use that constant. Volume has to be measured in liters. And then T is temperature, which has to be in Kelvin. That leaves us with just N, and N refers to the number of moles of gas. How much do we have? So there's all your pieces. PV equals nRT. Pressure times volume equals moles times a constant times temperature. Just like we did with the combined gas law, we can also manipulate the ideal gas law to solve for any variable. If we want to solve for pressure, P, underline the P, take everything opposite, and put it on top, nRT. Take what's with pressure and put it on the bottom, V. If I want to try it for another unit, say T. Let me erase this. Underline my T. Underline my T. What's opposite my temperature? PV. That goes on the top. What's with my temperature? NR. That goes on the bottom. I'll give you a chance to try volume and number of moles on your own. We would never solve for R because that's a constant. So let's try a problem. An underground cavern contains 224 liters of methane gas at a pressure of 7 atm and a temperature of 315 Kelvin. How many moles of CH4 are present? Okay, we know that it's an ideal gas law problem because of the word moles. It's the only equation we have that uses moles. So we're going to start with our PV equals nRT. Moles is N, so I'm going to rearrange it. N equals PV over RT. Now I'm going to fill in the blanks while I double check my unit. Pressure is 7 atms. ATMs is a good unit. Volume is 224 liters. That's the unit I want. R is our constant, 0.0821. And T is temperature. Temperature is already in Kelvin, so I can use my 315. Now if we take a second and calculate this, 7 times 224 divided by 0.0821 times 315 equals 60.6 moles of methane. Okay, let's try another one. If a balloon contains 0.0003 moles of helium at STP, what's the volume? The word moles lets me know we're using the ideal gas law. In this case, we're solving for volume. So PV equals nRT, V equals nRT over P. Let's start filling in the blanks. Our number of moles, 0.0003. R is a constant, 0.0821. Now it looks like we're missing a temperature, but we're really not. If you look at this little unit, STP, what does STP always tell us? 1 ATM and 273 Kelvin. So I can come over here and fill in 273 for my temperature. Pressure, 1 ATM. So to solve for volume here, 0.003 times 0.0821 times 273 equals 0.0067, and our unit of volume is always liters. So if you think about it, if I change that to milliliters by moving my decimal point 3 places, this is a 6.7 milliliter balloon. Tiny little balloon for a mouse. Okay, I'm going to have you try this problem on your own. What's the temperature in degrees Celsius of 2.5 moles of gas at 1400 millimeters of mercury occupying a 500 milliliter container? You're going to have to do some conversions and then use the ideal gas law. So in conclusion, what do we know about the ideal gas law? You need to have 3 of the following things: temperature, volume, pressure, and moles. And it's the word moles that lets you know you're using the ideal gas law. Your units have to be Kelvin, liters, atmospheres, and moles. Your equation is PV equals nRT, where R is 0.0821 if we're using these units. Make sure for each problem, give an answer and a unit. You can now do the last page in your homework packet.